In this video, K-means clustering of unsupervised learning in CUDA is a follow-up to the video An Introduction to Unsupervised Learning with a simple example in C++ that we posted a few weeks ago. We revisit the same example but implement it in CUDA. We'll first review K-means clustering. This is a unsupervised learning technique. It groups data points into clusters based on their similarity. So we group them into K groups. That's what this K means, or K clusters. Now, for example, suppose we have customer data with features such as age, income, shopping frequency. K-means clustering can group these customers into, say, 3 clusters. Cluster 1, young and budget-conscious customers. Cluster 2, middle-aged professionals. Cluster 3, high-income frequent shoppers. So this is the algorithm of the K-means clustering. So first, we randomly pick K central points. These central points are called centroids or means. Each data point is assigned to the closest centroid. Therefore, we obtain K clusters, as shown here. So these are unlabeled data. We cluster them into K clusters. And the data points at each cluster have similarity. And the cross here denote the centroids. And then we update the centroids by finding the average position of each cluster. So we get a new cluster center. And then we repeat the process. And the data, the centroids will converge, or the cluster will become stable. This is a CUDA implementation of K-means clustering. We discussed before that CUDA threads are organized into blocks and grids. A block contains one or more threads, and a grid contains one or more blocks, as shown in this diagram. So this is a grid of blocks, and so you have, say, 3 rows and 4 columns, and this is block 1, 2, row 1, column 2. It starts from 0, 0. And here the block index dot x is 2, block index dot y is 1. And for this block 1, 2, you could be 3-dimensional like this, or 2-dimensional, or 1-dimensional. So in this case, it is 3-dimensional. So block dim dot x is 5, and dot y is 4, 1, 2, 3, 4, and dot c is 3. And say for this thread, the index is idx dot x equals 1, dot y 2, dot c 0. So in our implementation, we will use one thread to associate with one point, and we use one-dimensional block. So the thread index is given by this. So I equals block idx dot x times block dim dot x plus thread idx dot x. That specifies a thread. So we define a header file. K means cu.h, okay, in which we define a struct, okay, point, okay, that specifies a point, the xy coordinates, and the cluster that it belongs to, and then a class called centroid. Again, it contains x, y, and also a default constructor. When we set up a centroid, we set the coordinates to be 0, 0. Okay. And the function k-means, okay, with parameters h points. H here means host. Okay. The points that we pass in, the h centroids, the centroids we pass back to the calling functions. Iterations, number of iterations that we want to perform on the algorithm. Yeah. Now, this is the program that does the k-means clustering. We include the header, and we define the threads per block to be 256. So one block has 256 threads. So this is a device function that calculates the distance from the point P to a centroid C. Okay, so it is straightforward. Basically, delta x square plus delta y square. And now this is the kernel function. Okay, we call it clusters that calculate the centroids. Okay. And we pass in the number of points, okay, from this array points, and endpoints is the number of points we consider. K is the value of K. K means here, this K means the number of centroids. Okay. So as we just mentioned, we associate one point with one thread, and the index of the thread is given by this formula. Okay. And if I is larger than or equal to n points, then we return. We don't use the more than n points thread. And we define the minimum distance to be a large number, to start with a large number, and the best cluster is 0. And then we calculate the distance between a point to a centroid, okay, and find the best cluster. Okay. And we say assign the cluster of that point, okay, to be the best cluster. Okay. So I, okay, corresponds to one thread. Okay. So that means we have all the threads, endpoints threads, working in parallel, working concurrently to evaluate the clusters. Now this is a host function that calls these kernel function clusters. So we call this k-means. H points is a vector that we pass in input parameter. Okay. Centroid H centroids is an output parameter. Okay. And iterations is the number of iterations we perform on the algorithm. So we start with n points, which is the size of H points, and k is the size of centroids. Okay. And now we divide the device array, okay, d points, okay, and d centroids. And then, as usual, we allocate memory, okay, using the CUDA manual. We discussed this many times before, and then copy the data, okay, to D points, okay. And then we iterations number of times. We call this function cluster to do the clusters to find the new centroids. So here we calculate the number of blocks, n blocks, to be the ceiling function of n points, number of points, divided by the threads per block. Okay. So it's one-dimensional. So that means we did that many number of blocks, okay, and that number of threads per block, okay, and we call this kernel function, passing the D points parameter, okay, and D centroids, okay, that's where the centroids are returned, and endpoints, okay, input parameter, k input parameter, and then we, as usual, we do the device synchronize, okay. And after that, we copy the data back to the host. And then we update the centroids. Okay, we declared the counts, okay, integer counts, and fill that with 0, okay, the array with 0, and we declared a new centroids, k new centroids. The default constructor will set the xy values to 0. So we sum up all the xy and also increment the corresponding count, and at the end we divide the corresponding centroids by the count. Okay. So we get the new centroids, and then we free, after the calculations, we free the arrays D points, D centroids. Okay. And now this is a routine for testing the k-means routine we mentioned here. Okay. So we include the header file, and we define some constants. Screen width to be 800, screen height to be 600 to limit the xy values to be within 0 to 800 and 0 to 600, and the number of points is 1000. Okay. And we divide the point vector, okay, vector points, okay, to hold the points, and this vector centroids to hold the centroids, and we just define the k value to be 3. Okay. So there will be 3 centroids. Okay. And this is the testing routine. Do k-means. We pass in points, the vector points, and the centroids. So here we start with some random numbers. Okay. So the within here, k is set to k value. Iteration is 20. Okay. So point vet we resize the endpoints, the point vet we define here, and so we set xy to be the random points, random values, okay, within the screen width and screen height range. Okay. And the cluster is of the point is randomly assigned to the value between 0 and k. Okay. For the centroid, we make the centroids of the k centroids to be the first k points. Just these are random, and then we call the k-means function to do the work. Okay. And this is the main function. Do k-means point vector centroids. Okay, we pass it to here. Okay, so the points is the point vector. Okay, centroid is the centroid, and we print out every 20 points to see the result, and we also print out the centroids. Okay. So we execute. So this is a sample output. So you can see that the points are assigned to different clusters. We have 3 clusters, okay, 0, 1, 2, okay, and these are the centroids. Okay. So we can check the profile, profile of the program, and using this command mvpro, okay. And so the time to call or to run these function clusters, the kernel function is about 3.7 microseconds. And if we modify the program and use only 1 thread, then when you check the profile, we'll find that the program, the kernel function, okay, requires about 1.6 millisecond to run. So there's a speed up factor of more than 400, okay, by doing this in parallel, okay, or 400 faster. Now let's copy and compile these programs. So copy this and paste it into this file. And we save it. So we got this k-means cu.h, and we copy this k-means.cu. So we create this file k-means.cu. Yes, so we've copied this, and we can compile it. mvcc minus c k-means.cu. And you can see that we've created this object file k-means.o, and let's copy the testing routine also, test k-means.cu. vi test k-means.cu. So paste it. So we have saved it. So now let's compile this. So mvcc minus c test k-means.cu. And you can see that we have created this object file also. So now let's link them together. mvcc -o test k-means .o. And we can execute test k-means. And as expected, okay, these are our outputs. Okay. And we can check the profile. Okay, so this is the average time to execute the cluster's kernel function. And now suppose we modify this to use one thread. Suppose we copy this to k-means 1.0. 1 means using only one thread. Okay. K-means 1.0. So what we need to do is to make a for loop here. So we use only one thread. Okay. So we need to have a for loop here. For I equals 0, I smaller than n points, I increment. And we do that for all the points. And here, so we just use one thread. Oh, sorry. One here. Save. And we can compile this. One. Okay. So now we got this object file also, so we link them together. mvcc -o test. Okay, means maybe we'll call this one. Link with k-means 1, in which we use only one thread. Okay, so we created this executable. So we execute. So we get similar results. And now we can check the profile. So you can see that the average about 25 milliseconds. Sorry. The average of using these clusters is about 1.6. Okay, 1.59. Okay, 1.6. So as compared to the other case, okay, 3.7. Okay, so it is a speed up of over 400. We can also use a simple graphical interface to display the clusters and points. Here's the routine. Test k-means g.co. G refers to graphics. So we define the same constants: screen width, screen height, endpoints, pawn vec, centroids, and the default k value is 3. Okay. And the testing routine do k-means, okay, is basically the same as before, except that we print out the pawns in the same routine. Okay. So it's basically the same as this testing routine. Okay. But here we add some graphics interface using OpenGL. So this is the typical OpenGL graphics routine. Okay. So we have the callback functions, keyboard, and display. And so there's the initialization. Okay. And draw dot is to draw one dot. Draw dots is to draw all the pawns saved in pawn vec. Okay. And display cluster is to display all the pawns in the vector pawns, and also the centroids in the vector centroids. So these are input parameters. So we first display the pawns, okay, using different colors, okay, red, green, blue, yellow, cyan, and black. Okay. And then we display the centroids. Using magenta, we use a particular large pawn size 15. Okay. As compared to 5 for other pawns. And there's the keyboard callback function. When we press C, then we display the clusters and pawns. Okay, we pass in the pawn vector and centroids vector. And when we press D, this is redundant. Okay. D, we draw all the dots. Okay. When we press a number, it's 3, we set the k value to be 3. If it is 4, we set it to 4. 5, set it 5. 6, we set it to 6. Okay. And then when we press K, we call the k-means, do k-means, or this one, for the to get the clusters. Okay. And so this is the graphical interface, and here's a sample graphics output. Okay. These are centroids. Okay. And the clusters are displayed with different colors. Now let's copy this program and compile it. So this is test means G. So we copy this. And so we paste it into a test mean G.cu. So this is the program we just copied. And again, we can compile this mvcc -c test ag .cu. So compose, and we just created this object file test k-means sg. So we can link this MySO test kg, and we just need to link the k-means.o, and also we need to link with and also of course this object and -l gl, the graphics library, GLU utility library. Okay, so we have created this executable. Okay. Let's execute this file .test k-means sg. So this is the screen window, and now I press the key K. So you can see that the default K value is 3, so we have 3 centroids, and these are the clusters. Okay. And now suppose I press the key D. It displays all the dots, all these dots, 1000 dots. And now suppose I press C, so it displays the clusters. So we have 3 clusters. This one, cluster 0, okay, and this is cluster 1, okay, red, green, blue, cluster 2, okay, cluster center 2. So 3 clusters. Now suppose I change my number of clusters to 5. Okay, I press the key 5. Okay, and then I press the key K. Okay, you can see that we have 5 clusters, and I can display the data again, D. Okay, and display the clusters. Okay, so you can see that we have 5 clusters. Okay, with different colors, and suppose I press the key 6, so the number of clusters now increases to 6, and I press K, so you can see that we are 6 cluster centers, 1, 2, 3, 4, 5, 6. Okay, and I come back here and I press the key D to display all the data points, and then C to display the clusters. Okay, so we can see that we have 6 clusters. Okay, with the associated cluster points, okay, using different colors. Okay, so this is the program, okay, that uses graphical interface. Okay. Now, if you feel that this video is helpful to you, please give it a like. Okay. I will see you in the next video. Okay. Thank you for watching. Okay. Bye.